So our goal in section 10.5 is to work with the inverse of a matrix. 10.5. This isn't straight up and down yet. Okay, a little bit better. Eventually, it'd be nice to be able to solve systems of equations kind of the same way we do with stuff like this. 7x equals 21. Now, most people would think of dividing both sides by 7, and that's fine. Let me take a slightly different approach and multiply by the reciprocal, or the inverse of 7. But it's getting at the same thing, right? When you multiply a number times its reciprocal, what happens? What do you get? You get 1. You get what's called the identity. And the identity times x is just x. So it'd be nice if we could solve our system of equations kind of like that. And that's where we're going to head to. We're going to work on trying to find solutions to our system of equations using the inverse of a matrix. So let's figure out, how do you find the inverse of a matrix? Well, take out your handout. This time we're going to look on the back side of things. Calculation for the inverse of a matrix is even more painful than multiplying matrices was. It is major unfun. But stick with me on this and we'll see what we can do. So if you have a matrix like this here, we'll call that matrix A, and you wanted to find its inverse, the first step in doing this by hand is to write down this matrix. Does anyone recognize this? What notation could I use for this? I3. Good, that's the identity matrix of the same dimension. Now, when you're trying to find an inverse matrix, the only time that you could find an inverse matrix is if your matrix is square. By that, I mean the same number of rows and the same number of columns. It can't be a rectangular array of numbers. Now, what we're going to do slowly is use our row operations just like we would in putting things in reduced row echelon form to transform this matrix into this one. And we're going to keep track of everything we do here kind of over here. And when we're all done, when we get down to finally having the inverse, or excuse me, having this to be I3, then this over here is going to be the inverse matrix. Now, the example that they chose here, or that I have here for you, is kind of really tedious. I think I remember the last time I taught this class, I spent about 20 minutes writing this problem for the exam to make sure it worked out super easy, like 3 or 4 steps. This one has a lot of steps, and it's above and beyond what we're going to have to worry about. But it's good practice because it's putting things first in row echelon form and then in reduced row echelon form. So the idea is to first get rid of these two things down here. You want to make all these things below the main diagonal 0. And you can do that by adding -2 times row 1 to row 2. And then 2 times row 1 added to row 3. So if you do that, then you get these matrices. But notice that on the right-hand side, that 2 times row 1 extends all the way over here, right? Because 2 times 1 is 2, added to the third row, 2 times 0, 2 times 0, etc. So we're kind of keeping track of the changes we make here. The next thing I'm going to do is make this one equal to a 1. And there's some play in this. You can adjust this. But that means just multiplying this row by 1/3. All right, so that brings us down to this line. And unfortunately, we've got fractions now. The good part, though, is that this is already done for you. The next thing I want to do is I want to get a 0 here. What would get a 0 here? Yeah, multiply this by 4 and add it to this row. If I multiply this by 1 and add it up here, I'll get a 0 there. And all these calculations are kind of mirrored on the right-hand side of this. Whatever you do, right. Whatever you do here, you're also going to do over here. Yeah, this one's a rough-looking example. A couple more things. So we got zeros here and here. The next thing is that to make this number here, it's called a pivot. Make that equal to 1. So you can multiply by the reciprocal here, 3/5. 3/5 has to multiply the entire row. 3/5 times 0 is 0. 3/5 times 0 is 0. 3/5 times 5/3 is 1, etc. 3/5 times negative 2/3 is going to be negative 2/5, and then 4/5, and then 3/5. So down here. Almost done. You've got to make these 0. You can do that by multiplying and adding. And finally, you get down to this point right here. All right, a lot of work. Let's practice with a couple smaller examples, a little bit friendlier. We'll start with problem number 12. So matrix A in problem number 12 is 3, 4, 7, 9. To find the inverse, I'll begin by writing 3, 4, 7, 9, and 1, 0, 0, 1. Okay, well, let's see. This one actually should work out even, although for a while we might get stuck with some fractions. It's just life. I would suggest you kind of follow the order that I'm going to work in. I'm going to make this a 1, then this a 0, then this a 1, then this a 0. So that's the order that we're going to make things. So A, B, C, and D. That's the order we're going to try and mimic these things. How could I make this first row, or how can I make this first element a 1? Well, I can multiply 1/3 times row 1. So what's that going to look like? Well, that's going to be 1, 4/3, 1/3, and 0. Now I didn't touch the second row, did I? So that's still the same. It's 7, 9, 0, and 1. All right. Let's stick to our game plan. I want to make this a 0. So how can I make this element a 0? Multiply row 1 by something and add it to row 2. Thank you. Negative 7 times row 1 plus row 2. So let's write that out because it's looking a little bit ugly. That's going to be negative 7 and then negative 28/3, negative 7/3, and 0. And I'm going to add that to 7, 9, 0, and 1. In fact, instead of 9, can anyone think of a better way I could write 9 so that I can add these two things together? Something over 3, good. It'd be 27/3. So when I add those together, I get 1, negative 1/3, excuse me, 0, negative 1/3, negative 7/3, and 1. And that's my new second row. One, 4/3, 1/3, 0, 0, 1/3, negative 7/3, and 1. Okay, making some progress. You got a couple choices here, that both of which are good. I could multiply this row by 3, and that'll put a 1 here, and that's going to be pretty good to have a 1 there.
Wait, don't you need to do a negative 1/3?
Is it a negative 1? Yeah, thank you, negative 1/3. All right, so we'll multiply this row by 3 then. So 3 times row 2 Negative 3, yeah, even better. Negative 3. So that gives me 1, 4/3, 1/3, and 0. 0, 1, negative 7, and negative 3. Almost done. There's one last thing that I got to get rid of, and that's the 4/3 up there. How can I get rid of the 4/3 up here? Where? All right, thank you. Last thing I need to do is I need to get a 0 up there so I can multiply row 2 by negative 4/3 and add it to row 1. So negative 4/3 times that is going to be 0, negative 4/3, negative 28/3, and let's see, negative 4? No, positive 4. And we're going to add that to row 1. Row 1 is currently 1, 4/3, 1/3, and 0. That's going to be negative 27/3, which is going to be negative 9. So 1, 0, negative 9, and 4, 0, 1, 7, and negative 3. So a little bit of a tortuous path, but that term right there is your inverse matrix. A lot of work is done in trying to find your inverse matrix. Depends on the matrix. Some of them are easier than others. If I put one on an exam like this, I'll definitely make sure it's one of the easier ones. Let's try problem number 18. And then I'll have something headed your way for which you can breathe a sigh of relief. By the way, any guesses if this is A inverse right here? What do you think I would get if I multiplied A times A inverse? Anyone? Yeah. The matrix equivalent of 1. So I2 in this case. All right, so problem number 18. Hang with me just a little bit longer. There is good news on the horizon. Victoria's skeptical. She's shaking her head. No, no. Trust me. There is good news on the horizon. We're getting really close. What's that?
We all get an A.
That'd be outstanding news. I would have nothing philosophically wrong with giving everyone all A's. I'd love to see that. Okay, so we've got a 3 by 3 matrix. 4, 3, 2, 3, 3, 2. Is it 4, 2, 3? Thank you. Little dyslexia amongst friends, never hurt. 4, 2, 3. Thanks, Kenny. And oh, I'd be at the end of this going, why didn't this work out even? These problems are challenging enough. I wouldn't give you one like this that didn't work out. Pretty straightforward. Now next to this, I need to write the identity matrix of order 3. Like that. Now, as far as a path through this matrix is concerned, I'm going to make it look like this one in this order. A, B, C, D, E, F, G, H, and I. Now, I might deviate from that a little bit, but that's roughly the order I'm going to work on. And I'm going to do something that you might think is cheating, but it's actually okay. The first goal here that I have is to have a 1 here. Now, one way to do that is to multiply through by 1/4. But the drawback on that is that you'd end up with fractions. Ugh. We had enough of fractions in problem number 12. So here's what I'm going to do instead. Let's just interchange row 3 and row 1. So I'll write 1, 0, 1, and then 0, 0, 1. Row 2 stay the same, so that'll stay the same here. And then row 3 is our former row 1. So, okay, I just changed things. In fact, if you were to multiply this matrix times this matrix, what you would see is that row 1 and row 3 would flop. It's effectively flipping this. And it's kind of giving you a hint at what you can do with digital photography if you had, say, a bitmap and you multiply it by a matrix. It's going to flip your image. You know, the right matrix, I would say. All right, let's keep going. So we got a 1 here. Let's get zeros here and here. So I'll multiply row 1 by -3 and add it to row 2. So 1, 0, 1. That's not going to change. 0, 0, 1. If I multiply this by -3, I'll end up with, and add it here, I'll end up with a 0. -3 times 0 added 3 is still 3. -3 times 1 added to 2 is -1. -3 times 0 added to 0 is still 0. Still a 1. And now a -3. So -3 times row 1 plus row 2. Let's do the same thing and get a 0 here. So -4 times row 1 added to row 3. Well, the first one's going to be a 0. Second one's going to be a 2. What else? So -4, that's going to be a -1. And, well, 0 times -4 is still 0, so I got a 1 there. 0 there, and then a -4 here. So I'm getting a little bit closer, which is good. And I want to help us get through this thing a little bit faster because I can sense a little impatience and like, oh my God, this is just the worst. All right, I understand. We're almost done. But one of my goals was to get this to look like that identity matrix. And there's a little bit of a trick that I can play here. It's going to help me out in a couple ways. I'm going to multiply row 3 by -1 and add it to row 2. And the advantage of that is that I don't have to deal with fractions. It's going to give me a 1 here, and that's going to help me out. So -1 times row 3 added to row 2. 1, 0, 1, 0, 0, 1. Row 3 isn't going to change. 0, 2, -1, 1, 0, -4. But let's see what happens when that should be row 3. 0, -2, 1, -1, 0, 4. So that's -1 times row 3 added to row 3 gives me 0, 1, 0, -1, 1, 7.
How do you get 0, 3, -1? Why isn't it 0, 2, -1?
Where? Here?
Yeah.
That's row 2.
Oh.
No, it's all right. Appreciate you checking me. Oh, excuse me. So 0. Yeah, I got to copy this row here now. So 0, 1, 0, and then -1, 1, 7. So we're getting closer. We're getting really close. There's only a couple more changes we need to make. I want to make this element a 0. So negative 2 times row 1 added to row, or negative 2 times row 2 added to row 3 is going to be 0, negative 2, 0, 2, negative 2, negative 14, added to 0, 2, negative 1, and then 1, 0, negative 4. Thanks. So 0, 0, negative 1, 3, negative 2, negative 18. That's going to be our new third row. The first two rows haven't changed. Zero, 0, 0, negative 1, 3, negative 2, and negative 18. Almost done. 2 more steps. In fact, when you do them at the same time. I want to get rid of the 1 here. And what's nice is that if I just add row 3 to row 1, I can do that. So row 3 plus row 1. The only thing that's going to change in the first part of this is that's going to be a 0. 1, 0, 0. And I'm just adding row 3 to row 1. So that makes this a 3, a negative 2, and a negative 17. Row 2 hasn't changed. It didn't need to change. And there's one last thing that I needed to do to clean up row 3. Yeah, times row 3 by negative 1. So yeah, kind of an inverse. So 0, 0, 1, negative 3, 2, and positive 18. Whew. Give yourself a star if your hand hasn't already fallen off and you're still awake. All right, so probably what we'll do on an exam is make a problem like that an extra credit question. But now it's time to take advantage of some technology. Okay, so there's our calculation for the inverse matrix there. But my goal here is not really to make you to suffer through a lot of long calculations like that. I want us to be able to solve systems of equations using an inverse matrix. And let me show you how that's going to be done. And then I'll show you a little bit of shortcut in terms of getting the inverse matrix. So let's talk about problem number 40 for the moment. Problem number 40 looks like this. 3x plus 4y equals 10. And then 7x plus 9y equals 20. Let's rewrite this using matrix notation. I can write this as 3, 4, 7, 9. So that's a 2 by 2 matrix times a 2 by 1 matrix. And I'll call this one capital X equals 10 and 20. And I'll call that one B. You can check the dimensions here. This is a 2 by 2 matrix. This is a 2 by 1 matrix. If I multiply the 2 by 2 matrix, I'll get a 2 by 1. Or this 2 by 2 matrix times this 2 by 1, I'll get a 2 by 1 matrix. So here's my idea. If somehow I had the inverse of matrix A, let's take a look at what would happen if I multiplied both sides of this equation by A inverse. Now some of this is going to be kind of predictable. A number times its inverse, or a matrix times its inverse, is going to give you the identity. So it's going to give you the matrix version of 1. And essentially the matrix version of 1 times this is just going to be that matrix itself. So that matrix is my x and y. Those are my variables. To calculate the solution to this system of equations then, what I need to find is A inverse times B. So if I had A inverse somehow, then I can multiply A inverse times B. So let's do that for this system of equations here. Let's take and find A inverse. Now, we're not going to do this the old mechanical way. Let's put matrix A into our calculators, and then this will be matrix B into our calculators. Let's put them both in. So matrix A is now a 2 by 2 matrix. So 3, 4, 7, and 9. You've got to quit, so hit second quit and stop editing matrix A and then go back in and enter and edit matrix B. Matrix B is a 2 by 1. And when you're done there, again, quit. Now here's the part you've been waiting for. And I'm going to reward your patience, although I might incur your anger at the same time. We'll see. In order to solve the system equations, one way to do it is to use the inverse matrix. So let's type matrix A, hit second, and then A. So the question is, what's the inverse? Well, you ready? What's this button here? Reciprocal, right? Something to the negative first power. Let's hit that. If you hit that, then boom, you get the inverse, just like that. Yeah, I know. You're like, really? We sat here for 15 minutes? I'm sorry. But to finish solving this then, you can do A inverse times B. So let's do A inverse. You don't need to hit the times key, and then just type matrix B, and there you go. There's your solution. Negative 23 and 18. All right. A couple people are mad at me. Sorry. But it's kind of nice. You get your solution pretty quick. A inverse B is negative 23 and 18. What's nice is that you can kind of scale this up. This doesn't just apply to 2 by 2 equations. It applies to bigger equations. And let's see if we can't scale it up a couple ways. Let's try problem number 44. So problem 44 is this. 5x plus 7y plus... Yeah, I know. That's why we didn't do 18 again. So yeah, so at home, you can figure out what we did wrong with problem number 18 because we didn't get that one right. 5x plus 7y plus 4z equals 1. 3x minus y plus 3z equals 1. And 6x plus 7y plus 5z equals 1. So we want to write this system of equations using matrices. So I want to write it in the form of ax equals b. Keegan, what would matrix A be for something like this?
5 7 4.
Mm-hmm.
And then 3 negative 1 3.
Good.
6 7 5.
Perfect. How about matrix B? What's that going to equal? Anyone? 1 1 1. So let's enter these into our calculator and solve a 3x3 system of equations faster than you've ever solved it. So matrix, edit. This time matrix A is a 3x3 matrix. 5 7 4, 3 negative 1 3, 6 7 and 5. After you've entered matrix A, make sure you exit, quit. Don't try and enter matrix B yet. So you want to quit, then go back in and enter matrix B, which now is going to be a 3x1 matrix. And it's probably worth practicing again. So let's do A inverse times B. It's not a bad idea just to print out matrix A. So just type matrix A and take a look at it, make sure you enter the correct coefficients. Matrix A inverse times matrix B. Wow. Pretty fast. Pretty cool. Alan? I think you got an 83. It might just do things a little different. Really? But did you do A inverse or A? You got to do A inverse. So if you take a careful look, what I do here is you hit matrix A and then you hit the x to the negative first power key. That gives you the inverse. So you want A inverse times B. So try that. See if that works for you. How about the rest of you guys? Are you able to get this one? Are you able to scale that up? I mean, because you can do that with like a problem like 46. You can do this with any dimension matrix. So in terms of solving systems of equations, all you have to do now is transfer them into matrix form so that you can multiply A inverse times B and solve them pretty quickly.
Is it giving you the values?
Yes. So this is X, Y, and Z. So yeah, our solution then is 8, negative 1, and negative 8. So matrix X, 8, negative 1, and negative 8. And you can check that these numbers fit in this equation. Let's just check the first one. You'd end up with 40 minus 7 minus 32. 40 minus 39 is 1. It checks. So it's kind of a nice quick way. Now, there is trouble in paradise, and we'll have to understand this next time. But let's take a look at problem number 26. Is it 26 or hang on? Yeah, problem number 26. Suppose I ask you to find the inverse matrix there. Problem 26 is a 4x4 matrix. Kind of a binary looking one. 1, 0, 1, 0, 0, 1, 0, 1, and then 1, 1, 1, 0, and finally 1's all the way across the bottom. So if you've kept up with me, great. It should look like this. Let's see what happens when we try and find the inverse matrix. So one more time just to look at that. And then let's try and find the inverse. Uh-oh. You can't always find the inverse of a matrix. Sometimes you have just the wrong conditions to find that. And we'll figure out in section 10.6 why sometimes it goes south when we're trying to find an inverse. But that can happen, so be aware of it. If that happens, what that's saying is that your corresponding system of equations either has no solution or an infinite number of solutions, one of those two. And we can determine that with Cramer's rule. For now, let me give you some homework. 3 through 13, 19 through 23, 27, 29, and 35 through 49. Those are just the odds. So that's section 10.5. See ya! Wow, and you're getting out early too.